Right, so welcome to the 10th lecture on random processes. What did we discuss last time? What was the topic mainly? Second moment, the variance. Yes. Today we will continue. Before that, of course, we have done the first moment. Yes. So today we will see the moments, these two moments, as operators, mathematical functions. Yeah, that operate on random variables. Yeah, and we will also see some very important concepts related to cousin of the variance, which is covariance. Yes, and because that naturally leads to more extended discussion on um, two variables and then more than two variables. Okay, so let's we have discussed variance in great detail. I know this is bit much time on that, but I want you to be very clear on all these foundations. Why? These are the terms, the words that keep on repeating in this field. Yeah, so you should have a very solid grasp on their mathematical roots and on their conceptual roots. That's why I'm spending some time on these. Otherwise, variance. How do people teach variance normally? They say, well, variance is Ex minus mu x square, right? It is summation if it is continuous x minus mu x square fx dx. बस फॉर्मूला लिखवाया उसको 15 solve it 15 ways and you're done. Right? But I don't want that, because this is for someone who's just familiar with let's say this is for mathematics technician kind of thing, person who just knows how to solve the formula or put some values here. This is not for someone who wants to do research in these things or be a mathematician, right? From in this branch, mathematical statistics, for example, machine learning, all that. So you really need to have those understandings, because in good research you will often come to situations which are new. Right? Now, if you keep making basic mistakes in those situations, you will never get anywhere. Yeah, you will make mistakes even when you know these things, but those mistakes will be bigger mistakes, like bigger in the sense that there will be mistakes on something that is actually hard, not on things that are easy. Yeah, and then you will spend time, repeat, and you will be able to solve that hard thing. But if you just keep making mistakes on the smaller things, then you may be able to solve that problem, but in so much time that it's not efficient anymore. So the first moment and the second moment, we will now see them as operators. So this is now an operator. Yeah, like functions in here. And similarly, the variance is going to be an operator. These guys take in random variables. So you may say, why not constant or determinate? We'll treat them as special case of random variables where probability is 100%. Yeah, so they can also be covered. That's not an issue, right? So firstly, when you read about functions and those things, you often study different properties in the deterministic maths. Yeah, so one of the properties of operators that we usually look at is it linear or not. So same here, we are interested, why do we go for these properties? We have the definition, why bother with properties? क्या फायदा होता है, क्यों बार बार करते हैं? Even in deterministic case, what's the use?
Because of problems जब हम solve करोगे lengthy problems, so then हम
analytical rigorous solution becomes easier knowing the properties, right? So that is the main reason. Yeah, so all these properties that we look at today are actually aimed at this thing, the mathematical roots of these and their conceptual foundations we have already done. Now, of course, we also need to deal with their solutions, analytically solving them, and that's where properties often come in very handy. Formulas or the definitions can be rather, you could always go back to definition and try to solve, but it will become too cumbersome. If you know the properties are shortcuts. in a way, yeah, mathematically sound shortcuts. We know they are correct, yeah, as long as the assumptions within the property are satisfied in your stage. We will see that. So this guy happens to be linear. Yeah. So what's a linear operator?
It preserves two properties with addition and scalar multiplication.
Yes. So it's homogeneous and it allows superposition. That thing. Summation. So in the general case, let's say I have a sum of k random variables. The small ones for now are deterministic constants. Yeah. So I is 1 to k. Let's say I'm just looking at this case. Yeah. So if it is linear, what will happen? You can exchange the summation and the product. Yes. So basically, it will become summation ai expected value of x I is 1 to k. Two things happened here. Firstly, this thing became within this whole thing. Yeah, that was 1. So the summation and these guys exchange position. Then the multiplier also was allowed to go out by homogeneity. Yeah, so it allows scaling. Yes, in that order. So now if you have ax1 some one random variable plus bx2 another random variable, now you know, you don't need to go back to saying it has to be ax1 plus bx2 times probability density functions of these and then do integration. No, if you already know their individual stuff, you need you just need to solve this as a e x1 plus b e x2. But there is an assumption here. What is that for this formula to hold? So look at the right hand side. To get this thing, these must be defined.
Yes,
Yes? Last time we saw there are random processes with density functions but without a defined mean. Yeah. So I will stop repeating that, but always know that when you are applying such properties, do not forget that there is this additional assumption that the things on the right hand side are well defined. If they are not, of course you don't know what to do with. This is undefined, then a times and what are you going to do? Yeah. So, but I'll stop repeating that. Just imagine this is always there. Okay, so it's linear. Yes, that's fine. What about the first we do this e guy. So that means the expected value of a scales linear combination, right, is the linear combination of the scaled expected values, right? So if you know that these exist and they were mu1 and mu2, if the means existed were defined and they were mu1 and mu2 for these two, so this is more like a divide and conquer now. Yeah, you first find the mean of this guy, then the mean of this guy, multiply those with a and b and add them, and you have this new variables, which is itself a random variable. Yeah, you have its mean without going into the basic properties. Yeah. Okay, so what about sometimes we are not just interested in the mean of a random variable, but also in the mean of the function of a random variable. So e of g of x, some function being applied to the random variable. What do you think will happen? Thoughts for you? Let's say for the discrete case, if this happens to be discrete, what should be the formula?
पास एक फंक्शन है, ये रैंडम वेरिएबल का, तो ये अगेन एक रैंडम वेरिएबल में कन्वर्ट हो जाएगा g of x. So that will be y p of x. It's kind of, अगर g of x को मैं y consider कर लूँ,
Okay.
वेरिएबल
So you want to call it y?
y
Yeah.
p of x.
So some, yeah, and p of?
Then it will probability of y.
Probability of
y.
y. So where will you get that?
p y y.
Who can say? So if I say, you can actually write it in probability mass function of x. Would that be okay?
ये ओके तो नहीं होगा सर, तो हमारे पास रैंडम वेरिएबल.
So I'm going to say this first. As I'm going to write it, then I'll do it. Yeah. This is my claim now.
Yes.
Sorry. This is whatever for all xi. Yeah. This is my claim. You almost did this. This was yi for you, and but then you want p yi. I'm saying pxi is enough. Okay. Why? This is where what we have been doing before this comes in handy. Go back to the very basic concept of the mean. Yeah. Was it, use anyone. Let's say you want to see it as the center of mass. Yeah. For example, or you want to see it as the expected worth. Yes. Now, if you are dealing with variable x, random variable, let's say x, and it had values x1, x2, x3, x4. I'm just giving one example. And each of them had probability x1, x2, x3, x4. Yes? How did you find the expected worth of this guy? You said, I will take what value it can take, multiply by with the likelihood of that value, plus I will take the other value that it can take, multiply by the likelihood of that, and so on. Now let's say I have defined g of x. For this case, let's say I have defined it as x square. So now what do you have here?
x1 square, x2 square, x3 square.
Now, when x4 occurs with whatever probability, does x4 square also occur?
Yes, sir.
Or not? So in previous cases, let's say this was 4. Yeah. So 4 occurs with the probability of px4. Yes. So 4 times 4, 16 will now happen. You will only, whenever this appears, you will map it into this
Square.
value.
Yes.
Yeah. So the probability isn't changing, or it could actually change if it is not a one-to-one mapping. Then 16 could appear in 2 places, but then you will of course include that, both of them. But overall, what's happened? Just look at this. I'll also tell you from the center of mass definition. But what's happened here is that the value it takes has changed, but the probability that that value shows up
Will remain so.
is same. And even if this value, because of square, maybe x1 and x3 were different, but x1 square and x3 square are the same, then it will add up anyway. So nothing to worry about. It will show up again. So the formula doesn't need to change,
Yes,
does it?
so we can just say we have defined a function, we have assigned random variables
Mapping कर देना.
on the basis of some random experiments, x1, x2, x3. So we are just changing our x1, x2, x3 values.
Yeah.
It's kind of
Now,
another mapping.
G is not a random function. G is a deterministic mapping.
Okay.
So
That is another
Yeah.
function that we define on the random experiment phase.
yeah, yeah. So if values were 1, 2, 3, 4, and they were gonna appear with probability 1 by 4, 1 by 4, 1 by 4, 1 by 4. Now instead of them, remember we talked about mapping omega. It wasn't unique.
Yeah.
This is just, you started with one mapping and then you thought, oh, no, I want to change my mapping. This is what you did. That's it. Yeah, nothing else. But this leads to this conclusion that you don't need to change this probability thing. Yeah? Kobayashi has a rigorous proof of this. Okay, because you need to prove that if the mapping is not 1 to 1, then these will add up to, again come back to this, but this is more of a conceptual proof. Same thing with center of mass. What was going to happen? Let's say you had x1 here, you had x2 here, you had x3 here, you had x4 here. Yes, and you are going to put the center of mass somewhere so that whatever probabilities they were appearing with, yes, was this thing. Now, because you have applied a function on them, you have changed your axis. Yes, so now they may not be in the same order. x1 was smaller than x2. Now gx1 may not be smaller than gx2. So whatever order they show up in, I'll just for my own convenience, I'll just write x1, let's say gx2, but the order could be different, whatever that is. But the probabilities here, the weights they apply remain the same. It's the moment arms that you are changing. Yes, and now find the mean. Now find, I'm not saying it will be exactly where it was before. You have to find it. Yeah, but this is what this formula is saying. It's saying leave the weights, leave the forces where they were, change the moment arms. Right. So in both ways, you see that this formulation makes sense for us. Okay. So continuous case, you can imagine it's the integral. So I won't write it. So what did we do so far? We said it's linear and that it's not really much affected by a deterministic transformation. Yeah, if there is a transformation, okay. Some new students or in undergrads, students sometimes think that E of G of X should be G of E of X. Yes. These are two operators. Yeah, this is a deterministic operator, this is a random operator. Yeah, so or operator on random variable there. In general, that is not the case. Linearity doesn't allow say that. Yeah, yeah. If G is a linear function, then you are back here, and then you can use that. Yeah, but in general, it's not true. This is true. You have to go back to definition in some form to get that. Right. So these two we have done. This is what happens when they are linear combinations. What happens when the mapping is some general mapping, G of X. Then what happens? So a function of a random variable. We call it the mean of a function of a random variable. Yeah, there is nothing special. Right. So let's see what else can we say about it. Another property is if the random variable happens to be greater or equal to 0, then we know that the mean should be what? Greater or equal to 0, right? Because of course, why is that?
Because probability is always greater or equal to 0 and summation will always be positive and product summation.
Yeah, or from central mass you could think that you are dealing with all positive values, so why would you put the wedge on the left? Right, so all of them are to the right of 0. Why would you ever imagine that this will balance here? Yes. Yeah, it should be there somewhere, whatever the distribution there. Now let's make it a bit more interesting. Okay, this is okay when x is greater than 0, then we call it the non-negativity the property, that when the random variable itself is non-negative, the mean is also non-negative. But now what happens if the random variable is almost surely non-negative? Ab kya aapka guess? What's your guess about this? Should it change or? You have to use all your knowledge of what we have been discussing. For the clear case, it makes sense perfectly. But what about almost surely case? याद है almost surely?
Yes, sir.
Almost surely याद है. Right.
So, sir, same here.
Same रहेगा. Why?
चलो सेम ही रहना चाहिए.
So yes, it will be unchanged remain this because it's almost surely positive or non-negative. So the mean, that means in infinite places it is greater or equal to 0, and only in a finite places it's negative. So it would
Most of our weight will be on the right side, so that's why.
so all infinite of those are if it's continuous and are here, then it's very hard to imagine that you will have to put this guy on the left. It will have to be still on the right. So the non-negativity actually applies not just to x being non-negative. If x is almost surely non-negative, then you can safely say. Right, what about this guy, multiplicity? Thoughts? Would they be equal?
Almost surely equal होगा sir.
No, this is almost. I'm not talking about this x greater or equal to 0 now. Yeah, that was separate. So this is 1, 2, 3. This is separate. For any two random variables, is the expectation operator separable like that?
Equal होंगे sir.
Sir, dependent or independent का
No, in general they are not.
Yes, sir.
Expected value is not separable. This is also a classic mistake students in undergrad especially make. They get two random variables, they make it easy for themselves and they say this. This is not going to be equal in general, okay? And we will see that where they can be where they can be equal. So unless okay, x and y are statistically independent. Often we skip this word statistically in this course when we say because independence can mean other things also actually. But in this course when we say independence we will mean statistical independence. So but sometimes I write it to emphasize unless x and y are. So what does that mean? Unless, that means if x and y are independent, then these are separable actually. Okay, so let's try to prove it or discuss it from how do we get here from independent. We're saying if they are independent, then this holds. Yes. So what is given? Independence.
Independency.
What has to be derived? This thing. Yeah, so you cannot start here. So now once independence is given, what do you know about independence in terms of probability, let's say mass function?
Probability mass function independency.
When two random variables are independent, what can we say about their joint mass function? We have done that.
The probability of x intersection y is equals to probability of x probability of y.
Yeah, so if I write it in mass functions, can I write it like this? Xi, yj is separable. Yeah, this is not coming from here. This is what we have to prove. Yeah, this is coming from the claim that if x and y are independent, then we already have discussed this as a test of independence, and this came from if you remember that same thing, probability A and B equals probability A times probability B, and that only holds for independent, and that in turn came from probability A given B equals probability A. Then we applied that
Condition.
additional formula and we came. So in a nutshell, independence, of course, this is a test, a very reliable test of independence. If this holds, then the two random variables depend. Now if this holds actually. Okay, so let's see. I can write this thing as j summation I xi yj probability xi yj. I'm multiplying both sides with the same thing. Yeah, this is given, but then I can, let's say, multiply out by xi yj probability xi probability yj. Now I've multiplied these out, but I can notice, yeah, this thing is what we will call exy. Yeah? By the definition, what's the, if you see the expected worth thing, the expected worth is the product, and what is the probability of that happening is the that x takes this value and y takes that value, so the joint PDF. So this is exy. What about the right hand side? I can separate it because there is xi and xi. There is yj and yj. So I can separate it into, let's say, for I can do xi pxi and times yj into pyj. This is, of course, Ex, and this is Ey. Yes, again with the assumption that, of course, these exist or they are defined. Yeah, so this will be Ex, this will be Ey. However, if you don't have this given that they are independent, you don't have this luxury, they are not separable, then you cannot start separating this like this, and you will not be able to get here.
So will the converse of theorem will true or not?
No. So Exy, where is it? We will see that. We will come to that. Yeah.
Good.
And when we will discuss covariance and the relation between covariance and independence, yeah, we will see that. But this way it is fine. Converse is generally does not hold. We will see that. But so okay, so the mean product of two random variables, their mean as an operator is not separable except for the special case when they are independent. Then it becomes simpler, and it's been following from, remember we saw in probability, then we saw in probability, like the measure here A and B was PA times PB if they were independent. Then we saw that in PMF, joint PMF was separable, and now we have seen consequences of that in the expectation operator, right? So independence is rather important thing. We will come to that or related to others. What about variance now? So let's first define it. So these are the four things we have discussed about the expectation operator. Now let's do a few things about the variance operator. So V of what is the definition?
Variance of x is
Expected value of x minus
x
square, and we often write that as sigma x square.
Yes.
Yeah, the mean we write mu x often. Okay, so do you know any other formula for variance? There is another one people normally teach. What's that?
Expectation of x square minus expectation of x whole square.
Right? It is
Yes, maybe.
Or okay, we will write it,
Expectation of x whole scale.
which is like saying mu x square. Yeah. Okay. So let's quickly on your sheet. Can you get from here to here? ये कलर्स कुछ डिफरेंट है ना, सेटिंग चेंज.
Sir,
हो गया?
Oh yeah.
So how did you do it?
sir, we open the formula.
Okay, you expanded the square.
Yes, sir.
Then did you use some property
Yes,
of
some property.
what property? You linearity.
Yes,
Yes.
linearity, yes,
Sometimes you use it without thinking about it,
Yes, sir.
but you used it. So
Yes,
if
sir.
it wasn't linear, you wouldn't be able to do it.
Yes, sir.
So you then were able to write 3 terms.
Yes, sir. Then
Yes.
we apply our property expectation of constant.
Yeah, you also applied that.
Yes, sir.
Yes. Mu x square is still a constant.
Yes.
Yeah. So that its mean is just itself.
Yes, sir.
Good. Then you apply linearity again.
Yes, sir.
When you had this e of 2x mu x, you
Yes,
applied linearity again to bring out 2 and mu x,
Yes.
and it was ex, and that led to
Minus mu square.
yes. So right, good. Now let's say we have 2 random variables x and y, and we define a new random variable.
Yes.
Okay, and I want you to find the variance of z. Given I'm going to give you that the means exist, okay, and variances exist. Okay, so find the variance of z.
Sir, we put this one.
Will it, by your guess, by the way, will it be variance operator, will it be linear?
Yes, sir.
Would it be a v x plus b v y?
Yes, sir. Linear also.
Sure.
No. No.
Look at it. Variance does not just have e, it is a square, it
Yes,
makes
sir.
it not.
तो स्क्वायर बाद में आ जाएगा a square of x हो जाएगा.
Yeah, वो तो है होगा, लेकिन फिर उसके बाद things will also happen because square brings in new terms also, right? Cross terms जो आ जाते हैं. So okay, try it. Yeah, in general this is not true. Okay, don't make this mistake. So I'm going to erase this now. Do it. Your solution will lead us to our next topic. Okay. Done?
Just a minute.
कहीं और तो ही निकल गए.
सर इस तरह किया कि पहले z की जो वैल्यू थी वो x की जगह पर थी. Yes, sir. फिर वो
Then you
formula-
got this
yes,
square
sir.
thing.
Square thing फिर हमने फार्मूला का z स्क्वायर प्लस mu स्क्वायर माइनस 2z mu x फिर z की वैल्यू जो पुट की फिर दिन ऑपरेटर अप्लाई की. फिर
So the first thing, what did you do? E is
yes sir z minus mu x
mu.
mu x mu z
Mu
square.
x mu y square. Mu x mu y.
So mu z.
z. Yes sir.
Let's start with that. Yeah, mu z square.
Square, yes sir.
So of course you will need mu z,
Yes,
but
sir.
since expectation is a linear operator,
Yes sir.
you can write it as, right?
Yes sir.
So basically mu z in your case then is,
Yes sir.
yeah,
Yes sir.
okay. So you can put that here
Yes.
later and z here. So you are able to put in place of z is ax plus by minus a mu x minus b mu,
Mu
y.
Yes sir.
and you're not done yet. Yeah, there is a square.
Sir, actually we have done this. First हमने ये फार्मूला को z square minus mu.
ठीक है, वो भी, that's
Yes,
also
sir.
fine.
That-
So then where did you end up? Now after this it's just mostly algebraic
Yes, sir.
juggling. So where did you end up finally?
and that mu.
Just to make some space for ourselves. Can I say that you ended up with this variance of ax plus by, which was our z,
Yes sir.
yes, was a square
S square. Yes sir.
E of
Mu-
x square.
v of,
Yes, sir.
Yes sir. V of x square.
huh?
Variance
E of x square minus E of x square.
That is v of x,
Yes,
yeah,
sir.
okay. Plus b
B
square.
variance of
So a square v of x plus b square v of y.
Yes.
Then
Minus.
that's the tricky part, huh?
Yes, sir. Minus
What
two.
was it? I'm
Minus-
going to write it, summarize it. Maybe you didn't write it in exactly this form, but this is what it should be. ऐसा कुछ है?
Yes sir.
Something like that.
Yes,
Yeah.
so expand हुआ है इसको close कर दीजिए.
चले हाँ, सब फैल गया. Right, it's fine. But you can bring it into this notation, I hope. So of course this is straightforward, and then you also got here. Now अब ये क्या बुला है?
Expectation of two random variables.
ये वो है covariance.
Covariance.
Yes, this term, or at least let's say we will, for our community, stick to this part, is the covariance of
X.
x, y, and we are going to now from one random variable to
And
two
random variables.
in this dimension. First, before going here, ये क्या बोला है? What would your answer be if I tell you that x and y are independent? Then how would this statement change?
Covariance will be
The first part will be same.
if the linear operator expectation of x expectation of y, then ये जीरो हो जाएगा ना सर कोवेरियंस हमारे पास तो हमारे पास जस्ट ये टर्म रह जाएगी
Yes.
क्योंकि अगर हम इसको एक्सपेंड करेंगे तो जीरो हो जाएगा सर
Why would that be? Because remember we said if x and y are independent, then the expectation operator is separable. Not in general, but then it is. Now, in general, you're not able to do anything about this. You gave it a new name, covariance x, y. But for the special case, when x and y are independent, you can do something about it. The two are separable. Not just they are separable, what they lead to is actually zero. You are looking at the mean of
X.
e of x minus e of mu x, which will be mu x, so mu x minus mu x and mu x minus. So this is zero. Yeah. So what does that lead to? We say
Yes, yes.
the variance of ax plus by is this plus this 2ab covariance of xy unless x and y are independent. When they are independent, it simplifies to something very small. This big guy disappears. So we already now know that this thing has something to do with independence. Yes? So that is where now we go. What is this guy?
That's why we study some independency because it reduces our space of dependence.
Yeah, not just that. There are many other reasons, practical reasons. We will see that. But yeah, analytically it helps a lot. Makes things a lot simpler. A lot of applications assume independence. Okay, and sometimes that assumption is an approximate assumption. But even with an being an approximate assumption, it simplifies the calculation so much that we still go with it. Even when we know that it's not exactly holding, we still go with it because it makes calculations very simple. Okay, but we don't always have to do that. Right. So then our next topic: what is covariance? Mean क्या था? The first moment was, what was it? Conceptually?
Yes, expected worth. Yeah.
Expected worth or
mass.
center of mass.
Yes.
Variance?
Measure of giant probabilities.
No, it's a spread.
Variance.
Variance. Variance is
Degree of spread. How
yes.
spread out the data is around the mean. Yeah? Good. Now we are in a new concept. This guy is, we already have a hint. It has some relation to dependence or independence, because if they are independent, this guy vanishes. So it has some relation there. That is definitely the case. But then what is that exactly? So आपने covariance पढ़ी हुई है? Covariance? वैसे पढ़ी हुई है? Formula पढ़ा. Right. यानी नहीं पढ़ी है. Okay. So never कभी भी never accept just the formula. Okay, this we are not technicians or like just formula ये डालो और get the value. Yeah. Okay. So what is the formula of covariance? Okay, I have written it already anyway. Yeah. This is the formula of covariance. Of course, we defined it. This term that was showing up, we called it covariance, and we noticed that it has some relation to independence. But then this is the formula. End of story. But then what does this formula really represent? अब आप इस formula को घूर के देखें, stare at it, and tell me what is covariance.
It's kind of a third dimensional object, you can say,
A relation between.
and it's being spreading from x and y both sides. That we can imagine in that sense.
So let's go into. I can take this away, this whole thing, so we have space. So covariance of x comma y for us is going to be what was it?
Expectation of
Fractation of x
x
minus.
minus mu x and y minus mu.
Yeah. Okay. So from here, what can you see? What's going on? When will this value be high?
Because of multiplication.
Giant probability.
Yeah, multiplication is there, but you could have multiplied 10 by 0.1
Yes.
to get high value. No? Fifth. Multiplication in pure mathematics, in normal language, multiplication is always leading to something bigger. Yeah? But in mathematics, it could lead to something much smaller if it's multiplied by a fraction. So what's happening? What makes this value large? When will covariance be large? And what makes this value small? When will covariance be small? We saw covariance was 0.
Sir, if
Yeah.
both are positive,
Mm-hmm.
then covariance is large. If both are negative,
It's also large,
yes, large.
but
If one
negative
is negative and one is positive, then
still
yes,
can be a
still.
large number. So what's going
Sir,
on?
if one is negative and one is positive,
Still a
then
large number.
Yeah.
Minus 10 times minus plus 10 is 100. Minus 100 in its worth, it's a large number.
yes.
Yeah. So I will write the other definition. Covariance, I will explain this one, but I want you to think of from the formula also. First I will summarize well. Like variance was the degree of spread.
Spread, right.
Yes? Covariance is the degree of linear statistical
And
relation
yes.
between two random variables. Linear, I will come back to why linear. Yeah. Why statistical? Because the relation has this operator from statistics. Yeah. But it's a degree of linear statistical relation between. At this point, this may not make too much sense to you. We will, of course, next few topics, we will go through the details. But before that, I want you to see when this linear statistical relation is high, when is it low from this formula. So you have thought about it. You have given it some.
At mean the variance is 0. For mean we are talking about.
Yeah.
And
When this value is large, this one, what's happening?
when we are away from the x and y.
No, alone this value.
Okay.
Just
When
think
we are
of
away
when this
from-
value is large. Large, I don't mean negative or positive. I mean the absolute of that. Yeah.
That when we are away from the mean
When x
is away.
goes
from
away from its
Mean.
mean. Yeah. When x goes really far away from its mean. Let's say x goes away 100 steps, left or right doesn't matter. From its mean. What is this one?
When y
When
away
y
from
is
the-
away
Y going away from its mean.
Yes.
Now to make this value, keep it large, it has to be multiplied by some large value.
Yes, a large number.
Let's say when x goes away from its mean and y doesn't go away from its mean much, just goes away by one step, 100. But if x goes away from its mean 100 step and y also goes away from its mean 100 or 1000 steps, this guy goes up.
Yes.
Yeah. But are these alone enough? No. There is this guy also.
Yes.
What does this bring in? Not just x going away from its mean 100 steps. What is the probability of x going away from its mean 100 steps? Yeah? That's the key thing. In a way, that is not alone, this will have to be joint. But this is what. And similarly, 1000, y goes away from its mean this much. But with what probability it goes away from its mean. Yeah. So if you want to understand it, I'll write it out and then that will make sense to you. This is the one way of looking at it, and the other way from the formula is, I'm writing it because it's important here. On average again because of this guy. Yeah.
Yes.
On average, when x deviates from its mean, when x deviates from its mean, does y also deviate from its mean? If your answer is yes, when x deviates from y really also goes away from its mean, and if y basically yeah, but if your answer is yeah, when on average when x deviates from its mean, now how far it goes and with what probability it goes there, then does y also replicate that behavior in some way? Yeah, then there is some
Dependence.
dependence.
Yes, sir.
There is some covariance. Variance means what? Varying means what? Changing.
Changing.
Covariance means what? Changing together. Yeah. If one of this guy is jumping around million, 2 million with probability 98%, this guy just sticks to 3 values. Yeah, doesn't change at all, just stays there. Then they are, yeah, this is varying, but they are not co-varying, not varying together. Okay, and notice the varying doesn't care about whether you go to the left of the mean or the right of the mean. So covariance can be negative or positive. Both have meaning. Both say that you are, if I go this way and you, whenever you see me going this way, you always go that way. Are we still correlated? Yes, because you are following my behavior some way. Yes. So from the maths here, this is what it's saying in a rough way. It's not very rigorous, I know. Yeah, on average, which is here, when x deviates from its mean, does y. What I mean is when x deviates a lot from its mean, does y also deviate a lot from? That's what we are saying. Yeah. So, right now back to degree of. Now you will now already agree with, because of this, you will agree that this is some sort of a statistical relation
between it.
that you already agreed. Now the only part left to explain is why I am saying it's a degree of linear statistical relation. Yeah. So actually the way this formulation is written, it can only cover the actual deviation but not the way it deviates. Okay, so I will draw this with some figures and explain it, but before that, what is correlation then? You have heard correlation?
Yes.
What is that? So I'll write out the formula, but then we can come to it, back to it again. It's just a normalization of correlation. So it doesn't have any new concept.
Pure variance or variance.
Is there a square root? I always forget. Let me see. Yeah.
एक सब थोड़ा सा स्केरी सा फार्मूला हमने देखा तो आई गेस वो ऑटो कोरिलेशन का था शायद वो बहुत बड़ा
होगा वो देखते हैं आगे. Right, so correlation is just normalized covariance. I'll come back to this. I just want to write it here. Why we normalize, what's the use, we'll come back. It is not just a exercise in making things harder. It has meaning actually. It has use. We'll come to that. But as long as you understand covariance as degree of linear statistical relationship, or in this sense, you got the main concept. Now, let me draw it. Let's say what are we talking about in terms of, let's say let's bring in an interesting example. Let's say I have given two students homeworks, A and B students, A and B. They got several homeworks over a course and their marks look like this. So A, student B. I am not giving them names because last one I gave Ali and this, that was last year, but now we have an Ali in the class. And we just keep that A and B. So A got marks in assignments. In assignment 1, 8 marks, 10, so on. B got marks 7, 10, 4, 1, 7, 1, 6, 8. कुछ नजर आ रहा है? क्या नजर आ रहा है? Do you see some pattern in there?
7, 8, 10, 10, 3, 4.
Pattern, yes sir.
What is it?
1 to 10.
There is a bit of one difference.
Okay.
1, 0, minus 1.
Yeah, you don't have to find the exact pattern. We're talking about statistics here.
Yes, sir.
Yeah. So compare A and B. What's going on?
There is a difference of 1 marks or 0 in each case.
Okay, but what does that say?
They are very much close in assignment marks.
So when A gets high, B also gets high. When A, whatever its mean is, when A deviates from its mean, up high or low, yeah, B also deviates from its mean, yeah. As this goes high, this guy also goes high. It doesn't have to go high, by the way. If it goes very high and this goes very low, there is also correlation. But we will come to. For now, I'll make it simpler. So what's going on? When this guy gets good marks, this guy gets good marks. Let's not. This is statistics, yeah. We don't talk about exactly 1 mark difference. But this is good mark, yes. This is good mark. Bad marks, very bad marks. Medium, very bad. Medium, good. What's going on? When this guy gets good, when A gets good marks, B gets good marks. What's going on? What could be the reason? Tell me. I have written 3 here. So, first I'll make it easy for you. Could be a coincidence. हो सकता है बस बच्चे तो यही कहेंगे स्टूडेंट तो यही कहेंगे they will say what else?
Papers might be easy or tough.
Yes, very good. It might be that the assignment, these are easy versus hard. Maybe these were easy and these were hard and these were just medium. Yes, so this is an external factor, nothing to do with these two guys. Yeah, it's just that the paper was hard, or this quiz was, or this assignment was hard and this was easy. What else? एक आप नहीं बता रहे जो अक्सर होता है
Same
assignment.
IQ, same learning ability. वो सर वो तो छापा लगता है.
Copy.
I want that. आप बताया नहीं जा रहे शर्मा रहे. Copying. Yeah, maybe A is copying from B or B is copying from A. ठीक है? So this is the external factor. This is internal. Yes. So this thing we call. I will come back to this also. Firstly, there is a correlation. Yes. Here I am looking at causes of the correlation or covariance. We use this word interchangeably. I showed you the formulas. They have similar things. So yeah, they do co-vary. That is clear. Yes, they do co-vary. When one is in the good band, the other is also in the good band. When one is in the medium band, the other is also when one is in the low band. They do co-vary. Now I'm saying at least 3 reasons could be there. Could be purely random coincidence. It could be that they are copying. That is, one is causing the other. Yes, if B is copying A, then A getting good marks, B getting good marks is caused by A's assignment. Yeah, so this is called causation.
Causation, yes.
It should be one reason. Alone correlation doesn't tell you which one you are. The practitioner, the person interpreting the results, has to decide, or in many cases we are unable to decide. Yeah, so we will come to that. But then the third one, often, or it can be that they are not actually causing each other, but a third thing is causing them. Yeah, so there is some external factor that is causing both of them, affecting both of them. What is that external factor? Easy or hard. Yeah, here in this case, A is causing B, or whoever is copying the other one. Yeah, so causation, external factor, or coincidence. Yeah, so this is but in each case they are correlated. Now what happens, the way this is defined, it only covers, see, there's no square, cube or anything, it only covers linear deviations. Okay, so from a statistical point of view, if I plot these guys, their marks, yeah, usually when we are dealing with two random variables, we often try to plot them as A, B, okay, and if you plot them A here, B here, you may get something like this if there are lots of assignments. What is this saying? When this point here means that when A is low, B is low. Yeah. When A is, this point says when A is high, the projection of B is also high. When A is on the medium, B is on the medium. Now look at it. Even though this is statistically spread out, yeah, it's not exactly a difference of one. In deterministic math you want a line or something, yeah. In stochastics you will not get a line, you will get a spread that looks like a linear trend, like this something, yeah. So these two are highly correlated.
It's a regression line.
Then you try to estimate that line, that's regression. How you do it is regression, yeah. But here I just want you to see, if you were to plot something like this, two variables, yeah. So when A goes up, B goes up, yes. Here, what would be another case where when A goes up, B goes down? How would that look? Yeah.
Yes.
So the spread should be like this. So this point is saying when A was high, B was low. When A was low, B was high. Yeah. This is also a very high degree of correlation. Okay. In some things actually have an inverse correlation. That is also information. If you know that variable x goes this way whenever variable y goes this way, now I tell you that variable y went this way. Can you say something about the other one? You can, because they are highly correlated. You know, if it went highly this way, that guy went that way. So this is also highly correlated, and actually the covariance here will come out to be negative, in negative large value. Yeah. But what happens? What should it look like if they have no correlation? So
Sir, all the points away from the line.
Are away from
The line. There is no correlation.
Yeah. So how do you put points away from the line? So yeah. Now there are instances where A got low marks, B got low marks. Okay. But then there are many instances where A got, let's say, high marks and B got low marks. And there are instances where B got, let's say, high marks, A got high marks, okay. But then there are many instances where B got low marks, B got low marks and A got high marks. Yeah, everything is there. No conclusion. You cannot say anything about their correlation now. Yeah. This kind of situation, if your data is spread out like this is because they are not showing any covariance happening together, either directly or the negative one, indirect. Yeah. So in that case, we say that they have no linear. These have strong linear relationship. This has strong linear relationship with the negative slope, positive slope. No linear relationship. Yeah, so no linear relationship, or the other one is they don't co-vary. When one goes up, does the other also go up? Yes, here that happens. When one goes up, the other always goes down. Yes, there is a linear. Here no, everything is happening. It's non-conclusive, or it's actually properly random here. So no relation or something. So here the covariance will be, or the correlation will be 0.
Actually, just I want to summarize that कि covariance जो है वो हमारे पास है, जिसका आपने एग्जांपल दी कि अगर x हमारे पास मूव कर रहा है far away from mean और y हमारे पास मूव नहीं कर रहा, तो covariance यहाँ 0 हो जाएगा हमारे पास. तो ये वो जी केस नहीं कि हमारे पास x बढ़ रहा है और y हमारे पास कम हो रहा है, इस तरह
डायरेक्ट रिलेशन है।
तो फिर कम होने का केस किस तरह देखेंगे सर इन दैट सेंस?
कम होने का in this formula, what do you mean by, what we mean by small or large is how much this value is large or small. Yeah, so let's say x is going away from its mean to the right. Yeah, x is, let's say, 100 steps to the right, and y is just one step to the left or right, then they are not strongly covariant. But if x is 100 steps to the right and y is 100 steps either to the right or to the left, if it happens both ways, right, then of course they will still cancel out, some plus and minus will cancel out. It has to be either this kind of relation or
this kind of
this one. Otherwise the average will make sure of that. If it's, let's say, in one case when x goes to the right by 100, y goes to the right by 100. In other case when x goes to the right by 200, y goes to the left by 200. Yeah, then again you will not find any correlation, because those terms will now start, there will be large terms but they will start cancelling out. Yeah, so again you won't be able to say much about their linear dependence or co-varying. Yes. Graphically this kind of should help you understand the situation. Yes, and a mix of these, something spread out, will mean that there is not much you can say statistically. Right. So quickly then, just summarizing the correlation thing. I wrote the formula for correlation,
Yes.
and I said it was normalized
Normalization of
covariance.
covariance.
So why do we normalize? In general, you have studied normalization, you know, in mathematics there are many different, you normalize the vector, you normalize a measure, you normalize so many things. Why do we normalize?
to get a unit of something.
Unit of something. So what's the use of that unit?
Because we can construct a structure on the basis of unit.
Hmm. Anything else? You know, one of the simplest normalization that people know, even who are not mathematicians, is percentage. Yeah, 10% of people do this, 10%, they know this. Yeah, percentage is normalizing. Yeah, so let's say I tell you that a student got 1000 marks. Okay, is this a good student or a bad student?
It depends कि किसमें कितने बचे.
So it leaves out something. Without normalization, you need to give me 2 bits of information. 1000 out of what? 5000 में से लिए हैं या 1100 में से लिए? It changes a lot. Yeah. Now I say a student got 95% marks. I normalized. You don't have to ask me anything else. Yes. From the normalized value, you know why? Why? Because you know that normalized value can go up to 100. That information is implied. Yes. So covariance, if I say the covariance between these two is 1,000,000, you know, actually you cannot say anything. Okay, because they might be variables that work with large values, there might be variables that work with small values, and they also covary. So does that mean their covariance doesn't have importance?
It's kind of efficiency of covariance you can say.
Or it's the normalization, in the sense that what happens now when we do this, look at this. What was the formula of correlation? Firstly, correlation is just normalization of covariance. Why do we normalize? So we get a simple reference. So what was the formula of correlation?
XY, covariance of XY, covariance of X.
Now I won't prove it here, but it can be proven that covariance will always be between minus 1 and 1. Okay, so like percentage 0 to 100%. Student got 99%, student got 10%. We know where the range is. When we say two random variables have correlation 0.9, that means they have a very high positive correlation. When I say they have minus 0.9, they have a very high negative, still very high correlation, but going in the opposite directions all the time. Yeah, that's fine, it's still information. What is not really good for us is when this is close to 0. Yeah, so absolute of this guy, you will try absolute and get Cauchy and all that, and you can actually show that this is less or equal to 1, which I have written out here. So the normalized thing makes our comparisons much more sensible, because then we can define ranges, in percentage. What is a good student who gets more than 80%? I can just say it. I don't have to say a good student is one who gets 1000 marks out of 1100, gets 1200 marks out of 1500. Right? I don't have to make this huge thing. So covariance itself can have very different ranges depending on where these guys are operating. Okay, these could be values of, say, mass of electrons, and these are already very small. Yeah, what big value can they give you? And they could be masses of planets, and you're dealing with large values. So the large and small, you may make you think that the covariance in terms of the molecules is small, and the covariance there, the linear relationship is high, whereas that's not the case. It's just that you are dealing with large values. So you normalize those. How do you normalize those? You divide by whatever those values on whatever their spread was. See the spread? It will bring it back to 1. Yeah. So now, how does this help? I can now give you a template. Actually, people have, let's say, defined systems. For example, I would say that you find not the covariance, you find the correlation, and you make your zones. Okay, if you are in this zone or this zone, you will say high correlation. If you are here, low correlation. This could be, depending on application, it could be 0.5, 0.3, whatever. And as you approach here, within some very small range, no correlation. Yeah. Now I can say this, but in covariance I cannot draw this thing, because I don't know what scales you are dealing with. Okay, so that is the thing. I thought we could finish it today, but I guess, when do we finish? We have time, yeah. This is 1 hour and 15 minutes. Yes, but recording is already. Okay, so we started at 11. Yeah, I forgot. Right, so we will come back to correlation a little bit next time, and we will see some more properties of this thing. I just want to mention this thing, why linear, as I said, I've tried to explain there. It cannot capture non-linear relations. Okay, so for example, we saw that there was the case where there was actually no relation. Yeah, but two random variables may have some sort of fixed relation. For example, if you plot out two random variables, x and y, and their, let's say, the plot or the way they are distributed comes out, I'm just making it easier for myself, comes out to be a circle. Now you can see that they are following a circle, approximately equation of a circle. But you know what their correlation will be, or the covariance?
0.
Okay, because they are covering everything. One is high, the other is low. One is low, the other is high. Everything is covered. It just becomes 0. So correlation cannot capture this behavior. Okay. Similarly, seasonal trends, use of electricity going up or down with heat in the city. Yeah, there can be seasonal trends, but correlation will say almost 0. Why? Again, it just sees things like this, or the other way. As soon as you deviate from this linearity, you just spread out, or you do some non-linear thing, it approaches zero. Then what do we do? That seems like a very big restriction. Yes, but actually it's not. We still work with correlation quite a lot. What people do who are working with statistical data, most often they first plot the data visually. Then they see, okay, there is this trend, sinusoidal trend, circular trend, some trend. They first remove the trend. Okay, so they find the trend, they model it as a raised cosine or sine, whatever it looks like, and then they subtract from this everything, and then what remains, does that spread out like this, or does that just go like this? Yeah. So you can always take away this deterministic trend or almost deterministic trend from your data, and then bring it back to where you can again work with correlations. So it's actually, even though it works with only linear relationship, it's still very heavily used, and it's very powerful tool. Yeah. So just one more thing I can mention here. I've already mentioned, when there is high correlation, what does that mean? The cause. Yeah. So let's see this correlation. This statement is rather important, and does not imply causation. If X and Y are highly correlated, it does not mean that X is affecting or causing Y. Okay, they might still be, like as I said, there could be a external variable. So one reason could be coincidence. Yeah. Other will is causation. Yes, cheating, for example, in that example. And then there could be external factor. So this is very important. Sometimes people mistake this thing. That one is causing the other. For example, in countries that have low GDP, yeah, the expected life, the average life span is lower. Yeah. Now, is GDP directly causing people to get sick and die early, or what's going on? So it's not directly. It's not a medical thing, that GDP. Yeah. What is happening is, when your GDP is low, you have a low quality of life. Yes. So the low quality of life affects your, say, the health care you get, the air you are breathing is polluted. So definitely, on average, you will die earlier. So now, there is an example, an interesting example. I think from Sweden. I saw this some long time ago. So they saw that in Sweden, when people eat a lot of ice cream, so ice cream consumption is ice cream consumption, and this is drowning accidents, people drowning. And you know, when they plotted it, they found this linear relation. Okay, again, correlation. There is correlation, yes, high linear relation. There is correlation. The question is, should we just say that eating ice cream causes drowning? आइसक्रीम खाने की वजह से वो डूब रहे हैं, क्या हो रहा है? When people eat more ice cream, there are more drowning accidents. What's going on? So is eating ice cream causing drowning? Is this correlation? Does it really mean that causing there is causation, or something else is happening? What do you think? No. So what are the options? Coincidence?
Coincidence.
Yeah, could be coincidence. Causation? No. Very hard to imagine that eating ice cream will cause you to, if you go swimming after eating ice cream, you drown, unless the ice cream is toxic or something, and of course government won't allow that. So only thing left at the moment is external factor. People, when do people eat more ice cream?
Summer.
When do they go swimming mostly? This is not Karachi, yeah, so you can go in winter, maybe, but in Sweden it's -20 or something. So you can only go swimming in summer, and that also in a few days. Zyadatar summer mein pani is still cold. Okay, so only a few days in summer you get the water warm enough to swim in it. So people go out swimming in summer and they eat a lot of ice cream. So if you plot the two data, they show very high correlation. But that does not mean that eating ice cream is causing that drowning. There is an external factor which is causing both of them to go up or down, which is the weather outside. Summer, both go up, winter, both go down. Not that one is sending the other one up or down. Yeah. So correlation does not imply causation. And let me mention this one, last one, and then we are just ready to go to the next topic, which will be going from 2 variables to many variables. Yeah, so I can have that. We said independence implies
Correlation.
uncorrelation. Yeah.
Yes.
So if they are independent, we saw that. Yeah.
Yes.
We started with the joint probability being separable and came to Ex, the curve, remember, xy being
Yes, yes.
0.
Yes.
Okay. So independence implies uncorrelated, but uncorrelated
Does not imply independence.
does not imply independence. What does that mean mathematically? Which one is stronger? So I'm going to write this important statement here. Correlation is weaker than dependence. Okay? If two random variables are dependent, they are definitely correlated. But if they are correlated, you cannot be sure if they are dependent or not. Okay, so causation sorry, this is a different one. Independence is a much stronger condition. When they are independent, they have to be uncorrelated. You can prove it. Yeah, but the other way, as you asked before, it doesn't go that way. A simplest example could be that the dependence could be nonlinear. What would be the correlation? 0, because it is only a linear measure, or measure of linear dependence, but they are dependent. Your correlation says gives you value 0. Why? Because they were non-linearly depending on each other. But if they are independent, it is definitely the case. So remember, we said when they are uncorrelated, you have Ex, Ey equals mu x, mu y, and then we saw that covariance xy in that case, the Ex minus mu x time became 0. We already did that. And this, remember, we were able to get this from the probability xi yj. The joint probability was separable, right? When we said that x and y are independent, we were able to write this by definition of independence, and we were able to translate it into this. But if we are able to translate into this, then we can easily prove that covariance will be 0. But going upward, it's not going to happen. You can try it and read in Kobayashi if you want. So again, for uncorrelated case, if x and y are uncorrelated, then you get the simpler formulation. v square v y. If they are uncorrelated. If they are correlated, then you have to have, was it plus or minus? I forget. Plus.
Covariance.
Covariance. Yeah, which has its definition. So to summarize very briefly, we said that the expectation operator is linear. Yes, it is not generally separable unless they are independent, and the E of g of x is not g of e of x in general, but we wrote the formula for that, whatever it was. And then we saw for variance operator is not linear. Yes, and it led to something bigger like this, which led to the concept of covariance. Covariance turned out to be the degree of linear relation. As I said, on average, if x goes away from its mean, does y also go away from its mean on average? Yeah. And then we said that the interpretation of correlation was normalization of covariance, so that you know now you're -1 to 1, and correlation does not imply causation. So if you see things happening at the same time, don't assume that one is causing the other. Okay, could be a coincidence or an external factor. So correlation does not imply causation. That's one thing. And like they say, people when they smoke, for example, they die early. Yeah, but some people argue because if you cannot show an exact mutation happening in the, now they have shown, but I think if you cannot show exactly mutation happening that will cause cancer or something, you cannot say that smoking itself is causing early death. It could be that people who smoke are generally not too conscious about their health. You see, so there could be many different reasons for these things. So correlation does not imply causation. And lastly, this is also very important. What is the relation between correlation and dependence? Well, this guy is much stronger. Dependence is much stronger than correlation. Correlation is weaker. So independence implies uncorrelated, no, you cannot go backwards. This is bigger, this leads here, but this does not always go. I gave you the example. If these don't have a linear dependence, and so they are still dependent, but because it measures only linear dependence, it will show you 0. Yeah. So next time, inshallah, we go from 2 to many random variables, and with that we will be ready to, as soon as we go from 2 to many random variables, we are now going to random process. Yeah, finally we start random process, inshallah. But all of this has been a journey towards that. It is very important to make notes of these in your own words and lock these concepts. Yeah. So I think it'll take a lot of time. Thank you.